Swayam Prabha. Digital India. Educated India.
The other important topic that we would like to look at before we go into weight, how to initialize weights, is the learning rate decay. Again, here the idea is, because the neural networks, it is a very complicated function of the weights, it is very difficult to say when we are near optimal minima and when we are near some very poor minima. So, there must be some systematic way of changing your way, your learning rate. This is basically your alpha that you are pretty much used to, that is, you must have seen x goes to x minus alpha delta L over delta x, or in this case weights, you are used to weights. So, u w minus alpha delta L over delta w, right. So, this alpha. Okay. So, this alpha is in this many what people typically do is to vary this alpha with every iteration or epoch. So, what do you mean by epoch? Epoch is when you have gone through your entire data set. Epoch is when you have gone through your entire data set once. That is one epoch, right. Let us say you are using stochastic gradient descent or mini batch gradient descent. You have to run through your entire data set, and that will be considered as one epoch. So, from epoch to epoch you can vary your learning rate. This is important because this learning rate will dictate how much you change your parameters by, right, because the magnitude of the update also depends on not only on the gradient of the loss function with respect to the weights, but also on the learning rate alpha. So, by modulating alpha, you can also modulate the magnitude of your updates. Okay. So, what happens is that when you have very high learning rates, right. So, let us say alpha is a very large number, let us say close to 1, then your parameter values would vary rapidly. Okay. They would vary rapidly and by large amounts and would not settle down in a local minima. However, lower learning rate would lead to slow learning, which means that the parameters will not change rapidly, and it is quite possible that they can get stuck in some false minima. Okay. So, then there is no good way to know when to do what, but typically there are the technique that people use is to decrease the learning rate as the number of iterations or epochs increase. So, there are many ways to do that, right. So, one of them would be to reduce the learning rate by a constant factor every epoch or every k epoch, sorry, there is a spelling mistake here, or every k epochs. So, this is again decided by you. You have to again, this is one, consider this as another hyperparameter that you have to optimize, right. Another way would be to check the validation. So, you have validation data and training data. So, you check the performance on the validation data, and whenever the performance on the validation data improves, you decrease the learning rate by a certain fixed factor. Okay, what that factor is, of course, has to be determined by trial and error or some systematic search that we saw earlier. Okay. One of the more automated ways are also to ensure a very smooth decay. So, for instance, in the previous techniques we saw you manually or not manually, you you decrease the learning rate by a fixed amount, by a fixed factor every epoch. Here this is more a smooth way of decreasing the learning rate, right. So, so this is your initial learning rate which you set. Again, this is another hyperparameter that you have to figure out, divided by 1 plus there is some decay rate times the epoch number. Okay. So, as the number of epochs increase, depending on the magnitude of the decay, your initial learning rate will also decrease. Okay. This is a very smooth way of decreasing your learning rate. There are also exponential schemes for decaying your learning rate. So, that is also possible. Many of the software packages have these implemented as block boxes. You are welcome to use. Of course, you should know what you are doing. There is no reason why we are explaining this here. Okay. The next topic is weight initialization. Okay. So, this is again a very important topic, because if you do not initialize the weights properly, then you will not get good convergence. We will see why that happens, and then you have to keep trying out different starting points to train your network again and again to before you finally hit on some initialization that actually works. Okay. So, why is this important? Because in a typical neural network there are large number of weights, okay, hundreds of thousands of weights for a very small ANN, going up to millions and millions of weights for large neural networks, right. So, which leads to a large search space, right. So, search space is because you have to minimize your loss function, and loss function is a function of your weights. So, it is a multidimensional problem that you are solving, and so if you want to optimize that loss function, then it is a very large search space of weights. So, you are looking for a combination of 100 million weights or more, which will actually work, and you want the weights must be initialized randomly because to prevent convergence to false minima and also to explore the entire space. Just as we saw as to how we have to pick your range of hyperparameters for hyperparameter optimization, we also have to figure out the range of weights that we have for the initialization, so that the entire space of loss function is covered, okay, to some extent at least, and that is required for an effective performance for a neural network. So, how is this typically done and what are the problems? A naive initialization would involve sampling weights from a Gaussian distribution or a uniform random distribution with 0 mean and unit variance, right. And so, your distribution of weights for one weight, let us say, or bunch of weights will look like this. So, this is W and this is the probability of W. Okay. Typically, this is a distribution from which you will pick, right. Now, we can do this, but there are some problems associated with this, and we will see what those problems are. Okay. Assume that your input data X has also been normalized. Remember, we normalized it Z-score normalization to have it 0 mean and unit standard deviation, and we are also picking weights so that they have 0 mean. And so, your weights Wi have 0 mean and unit variance. Your input features Xi also have 0 mean and unit variance, right. This we know. We also assume that the individual Xi are independent, Wi are independent. Note that this need not be individual Xi being independent need not be true, and subsequently the Wi also need not be independent, especially in the case of images where there is structure, but in most cases this is true. Okay. So, then what happens? So, let us say we have one layer, first input layer as Xi, and we have let us say m features, right. So, so your linear combination would give rise to summation Wi Xi, right, summation 1 over m and the summation of this, right. So, we just write this out. So, that will be, so this let us call this output y, right, or actually I will stick to notation and right. So, z is, so we will ignore the bias, okay, W naught. So, that is W1 x1 plus W2 x2 plus so on and so forth plus Wm xm. M is the number of features, let us talking about the first layer, right. So, the variance of z, it turns out under these assumptions that Wi are independent, Xi are independent, Wi and Xi are independent of each other, it turns out that then variance of z would be m times the variance of W's and times the variance of Xi, okay, that is what happens, okay, which is nothing but approximately, so in this case m. Okay. So, what does this mean? So, what is the implication? So, the implication is that if you randomly sample W's from a Gaussian with 0 mean and unit standard deviation, and you do, and of course, you have normalized your features also to be that way, then your variance on your sum that goes into the, that z remember is the input to your sigmoid function. Let us say, let us consider a sigmoid function just for sake of argument. M is the input to your sigmoid function. Then what happens, we saw that for large values of z, which is possible, right, because the variance of z is m times something, so it can take very large values. So, in which case then the sigmoid would saturate. So, during back propagation the derivative would be 0, and which means that the weights will not get updated. So, you are stuck. Okay. So, this is the problem with drawing from. So, but of course, this people have been doing this, and so you will have to do many trials and errors, so that at some point you will get one good combination which will let you do good back propagation. Okay. So, this is just looking at it from one input to a neuron, right. So, what we have discussed is, this is one neuron somewhere in the first layer, and all of these weights, these are the xi and these are the wi's feeding into it. Also recall that there will be neurons going from outside of them also. Okay. So, if you have, and say in this case I have used m features because we am assuming I am at the input layer. Typically we would say n in, instead of m I will say n in, which is basically the number of number of weights that are feeding into, or the number of neurons that are feeding into another neuron in the next layer. Okay. Another terminology is n out, which is the number of neurons or the weights emanating from a neuron in a layer. Okay. So, that is, you have to keep track of that. So, we have established that the variance of z, which is a z is a linear combination of the inputs to a neuron time multiplied by the weights. So, it is m times the m, it is pretty much m. So, it makes sense if we scale our choice of weights by m. So, the variance should be, so when we try to sample, we will sample from distribution with 0 mean and variance 1 over m, that makes sense. So, that is what people do. Okay. So, the variance of w, but from a previous argument would be about 1 over, in this n in I would call it, okay, which is basically the number of neurons that are feeding into a particular neuron. So, from a previous layer. Okay. So, this is n in. Of course, you know that the number of neurons also, number of weights coming in which from the neurons in the previous layer, and of course, from each neuron you have inputs going to multiple neurons as output, right. So, this number of outputs here we call n out. Okay. Now, we have only looked at the forward pass. In the previous arguments, you looked only at the forward pass and what happens. Now, it turns out that if you consider the backward pass, that is basically when you are doing back propagation and you want to preserve gradients, then, so then you have to keep track of, when you have to consider this number also, right, because the gradients feed in to each of these neurons from n out number of neurons, right. So, then what this Xavier initialization does, based on the author of the paper who proposed this initialization, is to make sure that the variance of w is the average of n in and n out. So, it is scaled by an average of n in and n out. So, which means that 2 over that. Okay. This is the solution they offer, and it turns out that it works very well for a wide variety of problems. Okay. So, in both these arguments, the idea is that when you have which consider the weights as independent and the features as independent, it turns out that the variance of the linear combination of them scales as the number of them, number of the weights or the number of neurons. And to take that into account, you scale the variance from which you scale the variance of the distribution from which you sample the weights by an appropriate factor. Okay. So, these are commonly used in practice. Xavier initialization is very commonly used in practice, and so is this one. The 1 over n in is also commonly used. Okay. So, both of them give very good results for convergence of a network very quickly. So, all of these, how they help is that they help fast training. Okay. Otherwise, it will take forever to converge, right, because you have the saturation, then the gradient becomes 0 because of the saturation, and finally back prop does not update the weights as effectively, and so the learning becomes very slow. By doing this initialization, we have will have effective learning. So, this ends our lecture on hyperparameter optimization, data normalization or data scaling as it is called, as well as weight initialization. Okay. If you have questions, please post them on the forum.